So in yesterday's lecture, we discussed about the PCA and SVD. Both of those techniques were uh, kind of unsupervised techniques because we were directly working on the features, and let's say there were different features: feature 1, feature 2, feature 3, feature 4, and we were uh, converting those features into a new dimension, right? And we were finding the covariance matrix, the eigenvalue, eigenvectors. So all those kind of decompositions were done. And we did not talk about the class, to which class they belong. The class was not there and target variable was not there. But in LDA, LDA is a supervised technique. PC was unsupervised technique, and PCA ignored the class labels. We did not need class labels to find the new directions, the new dimensions. We use the PCA, and it was called principal components. And the main motive was to maximize the variance in a data set. And similarly, I mean, kind of LDA is another method to get the work done, to bring the things into lower dimension, but it is a supervised technique, and it computes the directions, the linear discriminants that will represent the x's that maximize the separation between the multiple classes. Now I will discuss this point in detail on the next slide. And PCA that calculates eigenvalue and eigenvectors of covariance matrix, uh, but LDA gets these two values for within the class and between the class. So these two things are very important: within class and the between of two classes. So these two will be discussed in detail, and how these two are different. So we will be looking into, now let's see this first. PCA is the, I mean, new axis we have to get, and we have to maximize the variance, and we converted this x1 and x2, these two components, into lambda 1 and lambda 2, and we said that yes, this is the new dimension. But for LDA, the projection matters, to, I mean, from which side you are looking. If you look from the y-axis in this figure, obviously this is a bad projection on the y-axis because these two things are being overlapped, the blue and the green ovals. But on the x-axis, these two are good projections, and by looking it from the x-axis side, two classes are being well separated. Now I want to discuss some basics. First I want to discuss that how are PCA and SVD similar. So I want to discuss this, that how these are two similar. So first point is that they both are unsupervised techniques. We discussed both techniques in the previous lecture, and both of them were unsupervised techniques. And in this, what happened was, input features input features are projected into new space, are projected into new space, right? And the main motive of these two techniques was to maximize the variance around new principal components, right? So these were the basic things, and I will discuss this third point in more detail now. What was happening was, we were getting the new components, and after getting the new components, or you can say the vector matrix eigenvector matrix. So after getting this thing done, we said that each eigenvector column is new axis. So this was done, that each vector column was new axis, or we can say new direction, right? and both the things, these new axes and directions were maximized, in which the variance was maximized, in which variance was maximized. So these were the two things that I wanted to share about this thing. Maximize the variance around new principal components means that obviously we are getting the eigenvectors by calculating the covariance matrix and then the eigenvalues, and from that we were calculating the eigenvectors, and in the end we were multiplying the eigenvectors transpose with the original data transpose, or you were also doing the same thing by multiplying it directly, a into v, original data into the eigenvectors. So this was being done in the principal component analysis, and then each eigenvector column was a new axis. What we were doing was, now after getting this thing, uh, so this new direction means that the eigenvector was in this form, multiple vectors were there in the column form, and we were multiplying it with the original data, and the amount of variance is given by eigenvalue or eigenvector. Anyone? So the amount of variance is given by eigenvalue. Okay, so these were the basic things that you needed to understand about the PC and SVD. Both the algorithms were unsupervised, and in that, input features were projected into new space, and we had to maximize the variance around the principal components. So this was the basic of PC and SVD. But for the LDA, now how is this LDA different? Now LDA is a supervised technique, we have said that, and in this we need the labeled data. Labeled data is required, it is required in the LDA. Obviously the classes must be known, and you have to maximize the class separability. Maximize the class separability. Now obviously, because you have two classes, let's say these were the two classes, you had these first class and this one was the second class. So you have to divide this data set in a way that when you separate this with a straight line, it will be, I mean, the separability will be more. It is not that it always looks like this, but you have to convert it into a space in which you can maybe visualize it as, I mean, maybe like this. So these two are different. There is some separability also. One class is here, the other class is here. Obviously, I just want to demonstrate that you are converting the original data into new space. So this is the new space on the right hand side, and in this new space there is separability. Now you can say that, I mean, the basic thing is it is only applicable on the classified data. If the classification has been done in the data set, then only this LDA works. And once you can do this thing, let's say that you are able to convert the original data set into a space where you can classify or maybe improve the separability between the two classes, you can use the same technique. The LDA technique can be used for classification as well as regression also later on. But now the only last 2 points I want to discuss here is that, uh, I mean, between between the two classes, now these are the two classes, the separability has to be more, right? So interclass, this is interclass, right? Class 1 and class 2, this one is class 1, this one is class 2. So interclass, you have to maximize the covariance. You have to maximize the covariance, or this covariance can also be called as scatter matrix. Now obviously, because you want to improve the, you want to increase the separability, so you have to maximize the scatter matrix, and this is called interclass. And intra class, within the same class you have to minimize. So for a singular class you have to minimize the scatter matrix within the within the same class, within classes, within each class. So this was the basic thing that I wanted to discuss with you, so that you have more clarity. And let's see now stepwise working. All the steps have been demonstrated here, and we will be discussing one numerical also for LDA. Let's say that you have a data set with n data points that is classified into p classes, right? So there are number of p classes. So mu1, mu2, mu3, these have to be calculated. Means that you have to find a mean vector where each class mean will be calculated. So for class 1 the mean will be mu1, for class 2 mean will be mu2, and similarly for class p mean will be mu p. And you have to also calculate the global vector, global mean vector. Obviously it is very simple. So what you have to do is you have to find this mu, such that you have to do the summation of this mu I ranging from 1 to p, and then divide by p. So this will be the value of this mean, global mean, right? So this is how you have to do the first step. And then you have to compute the between class scatter matrix. Now between class, I was saying, between class means between the two classes you have to maximize this separability, right? So this can be done by getting this value. So you have to do the summation of class 1. So SBI here means that you have to do the summation of all the separability, I mean all the uh, what we say, between class scatter matrix. So you have to calculate for each class b1, b2, b3. So this is the formula. You have to calculate this value for each class, and then you have to do the summation to get the final SB value, final between class scatter matrix. Similarly, you have to calculate the within class scatter matrix. So it is denoted by SW, and this is the formula where you have to find this thing. In this you will be wondering that what is this Xij? Xij here means that it represents the ith sample in the jth class. Okay, let's say that this was the data. Let's say these are the 6 values, right? This is class 1, this is class 2, and within this class 1, this is the first element. So this is the ith value, means the first value of class 1. So j is my class and I is my location of that row. So here ij will be, we can say this is 1 1, and let's say we are talking about this one. So this one will be x of uh, 4 2, right? So I number is 4 here and class is 2, ij is 42. So this is how you need to get the formula. I mean, you have to work this formula for the dataset for those two classes. If we talk about the two classes, I will be showing you one example, numerical example, in which these two classes will be there, and you have to solve for everything. Now after this within class and between class scatter matrix being calculated, you have to compute the scatter matrix between from between class and within class variance given by this. Now you must be wondering that why this SW minus 1 is there and why this SB is there. So it is for a simple reason that you have to what we say, between each class you have to maximize the separability. So obviously this is a maximization problem if you directly use the value of SB. But SW, by default SW is your within class scatter matrix, and the values you have to minimize. So in, because you want to make this problem as a maximization problem, so that we can maximize the distance, maximize the separability, so we have taken inverse of SW. So that's why SW inverse has been taken, because by default SW is trying to minimize the separability, right? Because within class you have to minimize it. So we have, what we have done is we have multiplied both separabilities between class as it is, and SW within class you have to take the inverse, because obviously you want to make this I mean, you want to make this as a maximization problem as it is. So the next step is you have to compute the eigen values. Now obviously, if the matrix is given, you have to I mean, find the determinant of this matrix by doing this separability matrix, and then minus the lambda I, determinant equal to 0. So once you do this, you will find some lambda values, and you have to keep lambda only if it is significant enough. Let's say one value is coming out to be maybe 2.5, and the second value is coming out to be 0.0025. Obviously this one is very near to 0, we will discard this, we will only keep this. So you have to take care of this thing. Now sort the eigenvectors. So whatever you have calculated above, you have to sort the eigenvectors by decreasing the eigenvalues, and choose k eigenvectors within the largest eigenvalues to form p into k. I mean, the same thing has been written, that let's say that there are maybe five, seven, maybe seven different eigenvalues that you have got, but out of that only two were significant enough, and other five were very small, like this 0.0025, 0.00025, something like that, very low. So you have to keep only the first k eigenvectors out of it, and your dimension will be p into k. In that case, p is the number of classes, k is the dimension. So use this p into k eigenvector matrix to transform the samples into the new subspace. So you have to convert this into new sample subspace, and the overall new dimension will be coming out from the original data set. So let's see this small example. It will take 2-3 minutes to understand this example, and then we will move to the next thing. So this is what has been given to you. There are two different classes. There are two different classes. 5 into 2 and 6 into 2 are the dimensions of these two, uh, this w1 and w2. These are the two dimensions. So this is 5 into 2, this one is 6 into 2. Number of classes are 2 only, right? So this is first class, this is class 1, this is class 2. So this is how the original data set looks like. You have to convert this data into lower dimensional space. So what you have to do is you have to first calculate the mean of each class, mu1 and mu2, and global mean. So mu1 and mu2 will be found, you have to calculate the sum of these five, and this is 15 by 5 means 3, and similarly you have to calculate the mean of this is 18 by 5 equal to 3.6. Similarly these ones, and these are the values, 3 and 3.6 are the mean mu1, 4.67 and 2 are the mu2, and this is the global mean. You have to simply add this and divide by 2. Obviously you have to take care of the number of what we say, number of samples. So this one was having 5 samples in it, and 4.67 was having 6 samples in it. You have to divide it by 11, that will be the global mean. You will get the value as 3.91, and similarly 2.727 can be calculated on the right hand side. So this is how we calculate the mu1, mu2 and mu. Now the second step is to calculate the between class scatter matrix. So this is SB1, this is SB2, and this is the formula that was told earlier, n1 into mu1 minus mu transpose into mu1 minus mu. So by putting the values that we got earlier, you can get this matrix as 4.13. I mean, this has been solved for you, and similarly SB2 will be this side, and you have to calculate the overall between class scatter matrix. By doing the summation, it will be this third part. You can verify it on your end. Then you have to calculate the within class scatter matrix, and for that what you have to do is simply you have to do this process. You have to find the w1 minus mu1, w2 minus mu2. So by doing this you will get the values of within class, and then you have to calculate this thing, dj transpose into dj. So by, I mean, this is the formula of d, and it has been used here. in both the cases, and similarly you can find the transpose. So what is being done is you have to do this thing. SW1 will be transpose of this part into the original one. You will get this value. How? So this has dimension, this is 5 into 2, but the transpose of 5 into 2 will be 2 into 5, and obviously this one is again 5 into 2, so the second part is 5 into 2. The final multiplication will give you dimension of 2 into 2, which is same as this one. Similarly, the second part can be solved by I mean doing the transpose of this 6 into 2 into 2 into 6. Uh, so this one is transpose of 6 into 2, it will be 2 into 6, and second part is 6 into 2. Again the answer will be 2 into 2, which is in front of you. By doing the summation you will get this SW. Now we have got the SW as well as SB as the matrices. Now you have to compute the final scatter matrix by using this formula. I explained this earlier also. You are doing the inverse of within class scatter matrix. Why? Because by default scatter matrix within class is a minimization problem. You have to convert it into a maximization problem. So this will be solved by using this, and obviously I hope that you can solve, you can find the SW inverse from SW. The formula is simple. You have to do adjoint of SW divided by determinant of SW. For example, you have to, you have this SW as, I'm just giving an example. Let's say that SW is originally 1 2 3 4. Now you want to get the inverse, you have to solve it. I will only solve for adjoint. Adjoint can be found by exchanging these two and making the 2 and 3 as the minus, so it will be -2 -3. So this is how we get the adjoint, right? And you have to also do the determinant part, so it will be 1 into 4 -2 into 6, it will be -2. So this is how the adjoint is being calculated, and you have to divide by the determinant, so that's already done. So this is actually the final SW inverse. So determinant has also been calculated, and adjoint is also calculated. So minus 1 by 2 into this 4 -2 -3 1. So this is the SW inverse, and I hope you can solve it for yourself. The answer has been calculated for you. This one is giving answer as this, and then you have to compute the eigenvalues. You have to simply do this thing minus lambda I, and by putting the value you are getting these two values where 0.0027 will be discarded, it is very low. 2.78 will be kept, and then you have to calculate this thing, eigenvector out of it. So you have to simply multiply it by b1, and you have to calculate this eigenvector 1. It is 0.6 and minus 0.74. By multiplying this original data with v1 for both the cases w1 and w2, you are getting the new dimensions y1 and y2 as these values. So this was all about LDA. If you have any doubt you can ask, otherwise I will move to the next topic. ठीक है, तो let's continue with this new topic, sampling methods for supervised learning. It means that we have to make some samples. We have to do the partitioning of our original data into multiple parts so that we can get the work done from our model. So supervised learning occurs when an algorithm learns from example data and target associated responses. So it means that आपके पास features हैं और end में you have this target variable. You have both the things, then supervised learning happens. Supervised learning is where we have the input variables x and output variable is y, and this has been discussed earlier also. So I will move directly to these things. Now we can train our model using three methods. One method is holdout method, the second one is k-fold cross validation, third one is bootstrap sampling. So these are the three methods which can be used in supervised learning model. First method is holdout method, and holdout method means that you have to break your data set, the original data set, you have to split it into two parts, train and test. And it means simply that you will be, let's say you have 100 samples, you are randomly keeping 80 in one set and 20 in other set, but you will be training your model on these 80, and then you will be testing your model on these 20. Let's say आपने अपने model का, you have given this data set in which there is target variable also, and these 80 rows have been given for training, and the model has been learned and line has been fit, so something like this has been done. But for these 20, what you have to do is, when the data set is being uh, processed, you will skip the target variable. You are not giving this, you are just giving from 1 to n minus 1. These are the different columns that you will give for these 20, and you will get the predictions from this model कि भाई मुझे बताओ for these rows what is the output. So some output will come, so this is the output. Now this output will be actually compared with the original value that was maybe skipped at this stage. तो आपके पास ओरिजिनल डाटा में से जो जब आपने 20 लग किया था, यू हैड दोज वैल्यूज, आपके पास वो ओरिजिनल डाटा सेट में यू हैड द टारगेट वेरिएबल। तो जो आपने 20 निकाले भी थे आपके पास ओरिजिनल, तो उसका 20% का आंसर पड़ा है। सो दिस 20% जो ओरिजिनल था, यू हैव टू कंपेयर दिस ओरिजिनल 20 with the predicted 20, the output 20, and you have to check if it is exactly same, or maybe if one of the 20 is wrong, it means that 95% accuracy is there. I hope you are getting the basic idea what we are trying to do. So the training set is what the model is trained on, and the test set is used to see how well the model is being performing on the unseen data. A common split is, I mean, you can hold out using this method, maybe 70-30 partitioning, or maybe 80-20 partitioning. So you can keep the training data set as 70%, testing as 30%, maybe 80-20 भी आप रख सकते हो. So these are the common holdout methods. This is how we do the holdout method based supervised model training. I mean, this there is also one more concept called overfitting. It is modeling error. It means that, let's say you had these points that needed to be fit, and you took so much of time to train the data that you have remembered every point by heart. I mean, I'm talking about the model. So let's say that this is the machine learning model which has remembered every point by heart, and now if something new comes, let's say something here comes, and it is then it will not perform well. I mean, this is a simple example. It means that if you are cramming every point of the data set in the training, so जो भी आपका training data set है, if you're cramming every point while learning for a machine learning model, when a new point comes for prediction, you will not be able to predict it accurately. Why? Because you will expect that this point should fit into what you have learned. But if it is not, and it will not, in real world data set, every point is different, and you have to skip the overfitting. You have to avoid overfitting. So this is the basic idea, and let's see what's written. Overfitting is a modeling error that occurs when a function is too closely fit uh, to a limited set of data points. And overfitting the model generally takes the form of making an overly complex model to explain the behavior in the data under study. In reality, the data often studied has some degree of error, and originally ऐसा होता है that the original data set, because we have talked about this, that you have to remove the noise. We know that we have to remove the noise while doing the data pre-processing. You have to remove the missing values. You have to I mean, deal with the noisy data. If there is any noisy data, there can be a nan value, none value, there is even a nat value these days. So different values have to be there, and if you learn everything, you will be learning the noise also. So you don't want to learn the noise, you have to skip the random noise. So thus attempting to make the model conform too closely to slightly inaccurate data. So you don't want your model to learn the inaccurate data. That this will affect your model, this will infect your model with substantial errors. So errors will be coming while doing the prediction. So overfitting results in good performance with training data set, but poor performance with the test set. It means that when you are training, if you are overtraining your model, it might give you nearly 99% accuracy on your training data set, but when you're testing it on the rest of the 20 and you want to get the predictions, at that time it will do lots of errors, and maybe you are getting only 50% accuracy at test stage. And this gap between the training and test error, let's say in this case 49% gap, so this big gap will be a sign that overfitting has been done. And you can see here, I mean, example has been given. So overfitting can be avoided by holdback of a validation dataset, and using the resampling techniques like k-fold validation. So now different techniques which can avoid the overfitting, that has been discussed here, that you can do the holdback method for validation, and you can maybe use the k-fold cross validation method, remove the data points which have no predictive power maybe. So those kind of things can be done. So this side is good fit, good fit, both of these things, this one as well as this one, but these two on the right hand side are overfitting. These two are overfitting. So here you are cramming every point, right? You are going to every point and cramming everything, and again here you are making so much of curves, and you are actually overfitting your data. Lots of curves means that overfitting is being done. So you have to do something like this left hand side diagram in this case. So you have to not overfit, you don't have to do the overtraining, so that your model may be robust enough to do the predictions when new things come. Now let's discuss this holdout of a validation dataset strategy. It means that out of the training dataset, we were initially saying that we can do 80-20 training and testing. So this is training, this is testing. So out of this 80, maybe you can keep the validation dataset also. Out of this 80, maybe you can divide it into 60-20. It means that you have done a 75% and 25% split for this 80 training data. So now it's not just training and testing data, but you also have this validation data, and this will help you to actually make you ready for this test data set when it will be tested. So when evaluating a machine learning model, the validation step helps us find the best parameters for our model, while also preventing it from becoming overfitted. In this method, we have training set, test set, and validation set. So we have three things in this holdout method of a validation data set. So this validation set actually is a part of training set only, and it is used to build your model. It is actually used for parameter selection and to avoid the overfitting. So this is a good technique that will help you to reduce the overfitting. So pros and cons are there for this technique. Pros are that it is fully independent data, only needs to be run once, so has lower computational cost. But the cons is that it is subject to higher variance, because multiple small size data sets are being generated out of it. Let's discuss this k-fold cross validation. It is also very simple thing. I will explain it with the diagram first. You have to, let's say you have this data, and this is 20%, this is again 20%, and like this you have five different pockets of a data set, right? Let's say that there are total 100 samples, and you are keeping the first 20 as a holdout, and you are using the other 80 in this split one. You are using this 21 to 100. These are the 80 values that are being used for the training purposes, and this 20 will be shifted in the second split. The fold 2 is being hold out here, fold 3 is being hold out here, fold 4 is being hold out, and here fold 5 is being hold out for the test data. So this holdout method is being shifted from one space to the other between inside this five-fold cross validation process. So this is a five-fold method. There are five splits, and every time you are I mean five splits means that the data set has been what we say, This data set has been divided into 5 different subsets, and that subset is being selected one by one. And I mean, you will calculate accuracy. Let's say you are getting the accuracy every time, and let's say first time accuracy is 80%, second time it is 82%, third time it is 80% again, fourth time it is 79%, then last time it is again 83%. So in the end, what you will do is you will do the average of all these 5 accuracies, and you will get maybe accuracy of 81%. So something like this can be done, and this is how we can be sure that yes, my model is consistently performing around 81% by using this technique. So this is the basic idea behind the cross validation. And in k fold, k can be any number. It can be 5, it can be 3, it can be 10, it can be 100. So it the I mean, obviously pros and cons are there, and this will be time consuming, because you are now instead of training once, you are training 5 times, and then you are getting the answers in front of you. So cross validation or k-fold cross validation is when dataset is randomly split into k groups. One of the group is selected as the test set, and the rest are used as the training set. The model is trained on the test set and scored on the test set. So model is being trained on the training set. Yeah, so 80% of the data every time is being trained, and the rest of the 20% is being tested. So that's how we are getting the values, and I've explained the other points. So let's move ahead. I want to complete this k-fold, and we will continue the rest of the thing in the next lecture. So k-fold cross validation. So in this, a variant is one of the variant is leave one cross validation. It means that we leave one point out. So we leave the validation training for n minus 1 points. So out of n points, you are leaving 1 point, and n minus 1 points are being used for the training. And this is done for all the endpoints. So this is very time consuming. The pros is that it is prone to less variation. Obviously, when you are doing the average of multiple variations, multiple k folds, you are doing the average, the variation will be less. But it is highly computational. The model will be needed to be trained k times at the validation step. So this bootstrap sampling I will be starting in the next lecture. That's all for today, and we will meet in the next lecture on Monday.
Thank you, sir.